Um, so my name is Sin Sin. I'm the regional engineer on Eastern. Let me just share the slides now. Okay, off we go. Okay, so today I'm going to talk about technology and asset management from the network rail perspective. Okay, right. So during COVID, I think we have an explosion of innovation in terms of communications and digital technology. So our business had to undergo rapid digitalization. And then, for example, we started using a lot of um, online meeting software. We had so many different types: Zoom, GoTo, Google Meet, and Teams. In addition, in Network Rail, we had site access challenges at the same time, which means that our operating model had to change very quickly as well to reduce time spent by staff on track. So what I'm presenting today is a few of the case studies that we have progressed using technology to enable us to do inspection off track. Okay, so these case studies are cross-industry efficiency using in-service train data recording. So one of the best way of of not involving people on the track is to use trains we're running so often on the railway. So this is one of the case studies. And the second case study is about remote monitoring of S&C. And the third one is the Class 153 S&C inspection train using AVA as well on Eastern and on Southern. Okay. So the first one, cross-industry efficiency using in-service train data recording. I think this was started by Ellie Burrows. She's the route director on Anglia because she came from the talks and she said, can we work with the talks and come up with solutions for maintenance? So away we go. We worked with like 24 different talks and even some Roscoe's, and then to come up with solutions. So with a quick benefit study, we found that the main benefits were three different types of projects. One was to deploy the forward-facing videos nationally, and then the second one was to use UGMS data, and then with that we can redeploy our IM fleet, such as the PLPR nationally, and this could reduce about 200,000 hours of inspection on track, and also can reduce service affecting failure. And the third project was to monitor the OLE nationally, and that could reduce about 30,000 inspection hours on track. So in addition to reducing the inspection hours, we can also have other benefits such as incident recovery, access planning, site familiarization, all sorts of other benefits deriving from these three projects. Okay. So let's dive into the first project, forward-facing video. So in the beginning, we were looking at how much our IM fleet covers the network. So we found that it's about 60% of the network in daylight. So most of it is at nighttime. So we had to supplement it with TOC's fleet, the forward-facing videos from the TOC fleet. We had to look at the quality of the videos, and some of the cameras are quite old. So it has to be transported with using hard disk and all that to upload onto the system. So we had to upgrade some of the cameras as well. So last year we managed to like cover to improve the coverage to about 90% in daylight. And we use AVA system. I'm not sure if you're familiar with it. It's the automatic inspection video report video review. Okay, intelligent video review. So these are coverage is now about 90%, and a lot of our frontline staff use it to assess different types of activities, for example, vegetation, even sometimes track maintenance staff use it for to replace cab ride and also to do some handback of infrastructure and all that. So there are different use cases for this. So the second one was unattended geometry measurement system, which is in short UGMS. So we have about 16 trains now running on the country with UGMS fitted on it. We haven't been using it for the past 5 years. It was fitted like 5 years ago, but we haven't been using it. But from this study, there was a push to use it. So we came up with a strategy that all the main lines will have UGMS. For example, the West Coast Main Line, the Great Western Main Line, and for Eastern, we have the SPC, which is the Midland Main Line, the Anglia LTN1, and East Coast Main Line. We also have it on the TPE, which is the Trans-Pennine Express. So with this UGMS system, then we can move some of the IM fleet to the lower category lines. At the moment, low category lines are inspected manually. So that is a lot of manual hours that we can save if we can move our IM fleet to the lower category lines. Okay, so with this, we can save about 200,000 hours a year in inspection. So these are the fleet that we are fitting the UGMS. Some of them, as I said, are already operational. So for example, LNER, we have 6 operational, and TPE, now we have 2 operational. So so we'll be fitting more fleet, more trains, as I said, with the strategy of doing the main lines. So this is an example of the platform that we use to look at the UGMS data on the Eastern region. We use it on East Coast Main Line and the TPE Main Line. So as you can see, this is a snapshot that I took from the platform. It's called the RAVE platform. These are the data that was uploaded from Hitachi. For example, the first one was Hitachi TPE 002 train, and that was from the 26th of October. So normally when the train runs, the data would be available the next day. And working with Omnicom, Balfour Beatty, we sort of specify that we want the data to be daily. So we don't need like 2 sets of data a day, but daily would be useful because the train might be running up and down TPE twice a day. So we don't need that frequency. So with this data, you can see that, for example, the TPE 002, these are the data available. And then it runs from Liverpool all the way to Newcastle. So that's the data that we have. So this is an example of the traces we could upload. So there are 3 traces uploaded here. So I'm working with Omnicom to maybe change the colors a bit because the colors are so close to each other. It's difficult to see on the trace. But you can see you have 26th of October data, comparing it with the 19th and the 11th. So at the moment, the locational accuracy is not very accurate, as you can see at the dip angle at the chart there. They're slightly apart, but we are trialing it with the TMEs, and they're quite happy to use this because they know where the locations are. So even though the location may be over 20 meters out, they know where the problems are. So using this, we had already gained a lot of benefit. For example, on East Coast, they had a rough ride. I mean, it has been a very, very dry summer. So we have so many rough rides on Eastern. It's unbelievable. On East Coast, I think on one week, they had 16 rough rides. With rough rides, we have to stop the train and then we have to send someone out to look at the track and then to fix the track. And then we have to put a speed on until the next recording run to confirm that the repair has been completed and was effective. So with this UGMS, we could look at the track geometry the next day after repair, and then we confirm that it was better than the previous few days, and we could lift the speed up. So this example here, we lifted the speed 3 weeks before the next recording run, and that would have saved us delay minutes cost about £500,000. So it has proven that it's very, very useful. We have also used it to identify the exact location of where the rough ride was, and we could limit the speed, the TSR location extent. So that was a big help as well. Okay, so the third opportunity was for OLE monitoring. With this, we can save about 30,000 manual inspection hours. We had quite a poor performance in OLE in the last 3 months, I think we had at least 61. And so this would have helped us prevent any issues with OLE and capture them quicker before it happens, I guess. So we're working on this to roll out on the various main lines that we have. Okay. So this is the opportunity exists for OLE across the network. So this is what the IM team is currently progressing. So this data is like 6 months ago. So most of them, some of them would have progressed further than what is shown on this slide. Okay. So using in-service data, in-service train data recording, we estimated that we can save about £24 million per annum. That is including all these service affecting failures and in more efficient inspection method. Okay, so with this business case, we managed to secure some investment for the NR in infrastructure monitoring fleet program so that we can keep installing new equipment on in-service trains. Okay. So the next step is we're now monitoring benefits from installing these equipment. So the example that I've given about on the UGMS are just some of the examples that we are monitoring the benefits. Okay, so the next case study would be on remote monitoring of S&C. So this is very important because it gives us numerous data to see the condition of our asset. So there's so many sensors around. We product accepted quite a few different sensors. We have the YellTag, S&C switch system, and the Connaught system. So with Eastern, we have used different sensors. So this is a case study on how these sensors are useful. So this is a case study on a excessive vibration of a high-speed switch. So this is on HS1. So when I was in HS1, we have issues with this excessive vibration. So this is an example of a train running through a point machine at a speed of 186 miles per hour. So that's an Eurostar. So you could see that the vibration of the point machine was very excessive, and that caused a lot of failures in a point machine. We have components working loose. We have bolts cracking and all that. So we have issues and the bracket cracking as well. So that cost us a lot of delay minutes, performance issues. So the track, if you look at the track on its own, it's not vibrating as much. So we looked at it, the voiding was probably up to about 4 millimeters, not more than that. So but S&T and track had to work together to resolve this issue. So track went in and lift and pack that point machine area almost every other month, just to resolve this issue. But it keeps coming back. But we had 60 of these points, So why is it only 10 of them have this problem, but the other 50 does not? So we had to do some investigation. So we put a lot of sensors on the bracket. So these are sensors that are not very expensive. They're just accelerometers, the normal accelerometers. They're probably about £100 each. So we put them on different locations to see where is it that's occurring most vibration, and what is the natural frequency of the vibration? Because maybe the train passes is triggering the natural frequency of the bracket. In which case we need to redesign the bracket. So we asked the supplier, Vosflow, who's the point machine supplier, and they said they agreed to do some analysis. So they produce a finite element, a model of the bracket, and model it and show that the natural frequency of the bracket can be changed. So we found that for measurement, so you can see all the vibration measurement, that the natural frequency is about 24 hertz. So if you can redesign the bracket away from the 24 hertz, maybe this will solve the problem. Okay, so in parallel, so we went out to look at the point and look at, is there any other issues that we didn't pick up? So we did some profile measurement using the mini prof, which is very accurate, 0.05 mil accuracy. We found that there's actually a dip just near the swing nose. after well repair, it wasn't ground out properly. So there's a 1 millimeter dip in the rail profile at the well repaired section. So we went out and ground the swing nose, but we couldn't get rid of the 1 mil. We could make it lesser, reduce it to about 0.5 mil. So this is what was before. So after grinding, so the grinding worked, and it didn't come back for 6 months. So the vibration didn't come back for 6 months, but it did come back. So the problem was that the ballast was lifted and packed so much that it's rounded off. So the plan was then to renew the ballast. Okay, so lesson learned here is that you need to know what the root cause of the problem is. So our experience with Connox, on Eastern, we have quite a lot of these Connox device fitted. So especially in Doncaster. So the case study here would be the use of Connox at Doncaster. So Doncaster has 16 of these, and they were put on various crossings, on good performing ones and in poor performing ones, and at sites where access is very difficult. So this is a good performing crossing. Every dot of it is a train pass. So that's the maximum deflection. So you can see that the deflection over time is quite stable. So over a year, it's very stable. So that's a good crossing. So this Connox sensor is placed on the bearer. So it measures the movement of the bearer. Some of the sensors are placed on the rail itself. So it measures the movement of the rail. So because they measure different things, it's difficult to compare the sensor on the rail to the one on the bearer. So they measure different things, just to be aware of that. But we can use it for relative measurement. So this is a poor performing crossing. So you can see that the displacement is over 6 millimeters with every train pass. And this is just to demonstrate the maintenance effectiveness. So at the beginning, the voiding was quite substantial, over 4 mil, and then they did some manual repair. But the manual repair didn't last very long, maybe about a month, and it came back. So the depot decided that the manual repair wasn't worth it. So they planned in a tandem temp, which lasted longer. And this is an example of some maintenance work. They did some digging, replacing some ballast. So it was quite stable. And after the dig, it went up. But after temping, it stabilized again. So that's it. And this one is just to demonstrate what happened after reballasting. So the top graph is the acceleration, the middle graph is the displacement, the bottom graph is the speed of the train. So after reballasting, there's a TSR on the train, and then after the temping, you can see that the ballasts have stabilized, the displacement is quite constant, and we could lift the speed. So this is a good way of deciding when the ballasts have stabilized, the track has stabilized. Okay, so just some fancy photograph from Doncaster, Joshua Chambers, that is. So this is an example of how the performance of new crossing. So with a poor performing crossing, the displacement was high. And then when you change a new crossing, the displacement is low. So it's good, good crossing that we have there. And this one demonstrates that the vibration was quite high, but after well repair, it became worse. So the well repair has made it worse, which is not unusual. Okay, so using sensors, you have to understand the physics of what is being measured, the consistency of the measurements, and platform that converts data into useful information. So above all, what helps improve efficiency. So to us, what we have learned is that someone has to take ownership of the sensors and be monitoring and using the sensor data and convert it into useful information. Okay, so yeah, so someone in the depot has to look at all the platform, the dashboard, and decide what needs to be done. So that's the main thing. Okay, so the last case study here is the class 153 inspection train. So there are two of them running around in the network at the moment. So one is the eastern version and one is the southern version. So this class 153 inspection train is the purpose of this train is to supplement some of the BVIs, which is the basic visual inspection, and then also to measure some track geometry of at S&Cs, at low speed S&Cs at station areas. So what it does is that it has like six cameras at the bottom, all positioned at the location shown here. And then you have a Vista track geometry system, which measures some of the track geometry parameters. So we're not measuring the full suite of geometry system that we do in NMT. So we measure key ones, such as the gauge, which is very critical for Eastern, after like 4 white gauge derailment in 2020. Okay, so and then we have the forward-facing camera, and then we have a thermal camera as well. And then all these data collected from the train will go straight to the cloud after as and when it measures, and then being processed to the video and data on the laptop. So the whole process should take only less than an hour. So within the measurement of, we've been measuring an hour later, you get it on the laptop. So that's how it works. So that's the train. The Eastern train is actually colored in blue. Okay. And then this is the platform that we use. So the platform is very important, just like the Chronox sensors. The platform is easy to use, and you can see what's going on, convert the data into information. So this is showing the different route that it has taken, the ELR, mileage details, and the various camera view. So you can zoom in like this to do basic visual inspection. You have thermal camera image, and you have like adjustments on the right that you can adjust the brightness and the contrast and all that on different rails. And then you can zoom, you have the track geometry trace next to it, just to see where the dips. So what it's showing here is the curvature and the cross level. Okay. And then this is the patrol. So as I said, the purpose of this is to perform BVI, basic visual inspection. So we load in the patrol diagram, and then we can do the inspection using the video. I mean the footage. So every bit that you have inspected, it will be colored in blue, and the ones that you haven't inspected will be left in red. So you must go through all the video inspection to make sure that your inspection is complete. So there's a drop-down menu, like for example, here we see a missing clip. Then you can select the defect from the drop-down menu, a missing clip, as you go through the inspection. And then at the end of the inspection, it will produce a inspection report at the location where you found that there was a broken rail, for example, or missing clip. And if you click on the view button, it will show you all the photographs that was captured. Okay. So, and we're using this also for a camera on the site. For example, here we're inspecting the conductor rail. So yes, working with the class 153 team and the IM team has been a pleasure, and AI VR as well. So we can use all these automation and all these technology to understand the deterioration rate and failure modes and condition of assets so that we can identify the most appropriate technologies to improve asset performance and reliability. And also utilizing in service trains and appropriate recording and monitoring technologies. This will require working collaboration with suppliers, university and train operating companies, and converting data into useful information that can be understood and utilized by end users and railway maintenance. That's the biggest challenge. I think I've run ahead of my time. So I can, I'll just mention a few other projects that we're working on. For example, this is the ride monitoring on in-service trains widget that we developed in HS1. So over the summer, we had quite a few rough rides. So using this monitor, we can take on cab riding. We just put it on the floor, and then we can record through the cab ride where rough rides are encountered. So it's plotted on this map, as you can see. Red means it's uncomfortable. So we can track the changes over time. So the top right shows the measurements over time. So where it becomes very red, then we can start planning in preventative temping before it becomes very rough. So this is in collaboration with University of Birmingham. So we're also looking at drone inspection. So this is a hot topic at the moment. So this video shows an inspection of a S&C crossover. So the left image shows the thermal imaging. This will pick up any issues with points heating or bonding cables. And the image is very high definition, so you can zoom in and look at individual clips. So the only issue with the drone inspection is that it depends on the battery of the drone. Normally it's about 15 minutes. Also with, for example, this inspection, sometimes you have to take a few flights above this S&C on the site because this is only the plane above the top view. So you might have to go on the site on the right or the left just to look at the site of the crossings or the switches. Okay. So we're also progressing a non-intrusive track bed investigation technique to replace trawl holes. This is a So what we do is to hammer in a tube, which is only about 20 millimeters wide. Hammer the tube in, and while you're hammering it, the hammer has like sensors, strain gauges, so you can track the force that you're hammering it. So that gives you a cone resistance. So it tells you how difficult it is to hammer the tube in and give you a sort of like a mechanical property of the ground, the subgrade, the ballast and the subgrade. So, and then after you've done that, you can hammer it all the way down to 1.5 meters or up to 2 meters. So you have to specify it because that will mean that what length tube you bring to site. So it can be 1 meter length, 1.5 meter or 2 meters. Hammer it in. So after that, this is a video of the ballast. So after you hammer in, you take out the tube and replace it with a hollow tube with a endoscope in. So this is filming the ballast. So the hollow tube will have pocket slots on the side where you can look at the ballast. And this is showing it to be 0.4 meters below the rail level. So you can see that the ballast now are slightly rounded. And then you have more fines here. So at about 500 mil below ballast rail level. So these are just foul ballast. So we know that this side has foul ballast and should be renewed. Okay. So this is just one example of how useful this is. So for this one, we only recorded up to like 800 mil below the rail level. Okay, so other things that we can do during the pandemic, we could work closely with the Eurostar top train operators. We fitted some thermal camera and some accelerometer on the cab, on the bogie and on the axle, just to monitor what's happening with their wheels, because they are having a lot of squats on their wheels, and that's costing them a lot of money to turn the wheels. So working with them, we could put the instruments on quite quickly. During the pandemic, we put everything on within a month, and then within 2 months, we went through vehicle acceptance, safety cases, and we started running the trains. You can see this is flange contact. So we could identify where the high loading are on the infrastructure. Okay, so for example, these are the data we collected. We collected the speed of the train. It went up to 300 kilometers per hour, which is 186 miles per hour. We have the axle box acceleration. So if we put a limit of 20 G, we could see that there's only like 5 instances of acceleration on the axle box that's above 520 G. So we could focus our maintenance team on those, and we found that 3 of them are on S&Cs, and that explained why those S&Cs were failing quicker than the others. And we could track the bogie acceleration, and we can track the coach acceleration where the ride comfort is an issue. So it's useful using remote monitoring. And that's it from my presentation. Thank you.
Brilliant. Thanks, Sin Sin. I don't, if just for presentation purposes, can everybody just turn their cameras off apart from Sin Sin, if that's okay? Thank you. Does anybody want to put their hand up and come in for a question first? Otherwise, I'll go to Andrew's question in the chat. Anybody want to come in? Liam, go ahead, Liam.
Hi, Sin Sin. Great presentation, thank you. I'm interested in the Conux deflection monitoring on the reballasting sites. I'm just interested, has that data been used to compare different reballasting methods to see, for example, if the rail vac or the undercutter gives different or better results, and perhaps, you know, even if the DTS or how much the DTS improves that activity? Has that sort of analysis been done at all?
I don't think it has been, but I think it will be a good way of trying to see how effective these are. So if you want to talk to Doncaster Depot, and then we can start looking in more detail how these different methods, how effective they are.
Yeah, no, I'd be really interested in that. Thank you, Sin Sin.
Brilliant. Thanks, Liam. Anybody else got a question? Okay, so Andrew's put a question in around data acquisition, and obviously being enormous, and you know, how are you doing anything to automate the process?
Yeah, data acquisition is very, very important, you know, like sampling rate and all that. So yes, you have a lot of data. That's why it's important to convert the data into information. So like the Conux one, you probably sampled the data probably at least 200 hertz, because if you're running trains at 125 miles per hour, it means the train is running at 55 meters per second. So that means you need at least 100 data points per second. So you have to get the correct frequency. Then you have loads of data. But if you convert it into a platform, just showing you the maximum displacement or the information you require, you don't need the data. You just need the information that you require that you can use. Yeah.
I was interested to know any focus areas that you have, because if you compare the data 3 years ago, 5 years ago, 10 years ago, it's really snowballing now. And are there areas where the human users of data are really finding it difficult to get high quality transition into information and decision making? Where is the focus, say, for the development and research?
Okay. So I think there's all these predictive maintenance that we are working on. So maybe predicting the failure rate and all that. So we can, yeah. So is that what you're talking about, Andrew?
Well, you demonstrated a number of different application areas, and they're very rich in data. But yes, I mean, certainly trying to get some predictive capability in there, and getting perhaps into good human machine interfaces to make it easier to read the data. That seems to me to be something that would be valuable, and combinations of different background information and up-to-date data, that seems to have lots of possibilities for you.
Yes, that's definitely, we don't want to be swamped with data. So for example, the AI VR platform, we are incorporating an algorithm which does vegetation management. So it scans the trees and the growth rate and all that, and then flag it up when there's a problem. So we don't have to always look at the data.
Yeah, it's very clever. I've seen it here. Yeah. Thank you, Sin Sin.
Thank you, Andrew.
Yeah, thank you. Anybody else got any questions at all? I think that testament to the go on, Liam.
It's not a question, just an observation. Since I think regarding the Panda Pro, but I think I've seen a video now. I think they've got some technology which it's an automated, almost like a drill. It's that you can drill it in. So I think if people aren't keen on hammering the spike in, that there is now newer technology which makes that operation a bit easier.
Thanks, Liam. Yes, I haven't seen that, but yeah, it's nice. It's good to know.
Peter's interested in how these going to be applied with the Canucks system, is it? Did you want to?
I was saying, Ian, it was great to see some UK use of it, because I had a visit to Singlewell with Sin Sin and colleagues 3 years ago, so it's good to see it's now in use.
Yes, Peter. Yes, we couldn't use it at in HS1 because I think it required drilling and to insert the sensor onto the concrete sleepers when I was in HS1. So it wasn't, we couldn't do that in HS1. But now that we have other means of gluing it or like bonding it onto the sleepers, so it makes it viable, I think.
So we got a question coming around. How often do you not find the root cause? For example, of a rough ride, etc. And what do you do to keep on looking at this and do new analysis and measurement techniques?
Yes, I mean, I think half of the rough rides are no fault found, if you like. So, and we also found out that most of the rough rides, the track geometry are not actionable faults. So it's very difficult to pick it up. So, so it's only through the UGMS we see that, oh, suddenly there's before that wasn't that big, but now it's bigger now. So it is, it might be the cause of it, but it's not actionable. You know, so it's quite difficult. But root cause of the failure is important, like rough rides. Sometimes it's because there's a tree there, and then because it's been very dry, and that tree might have been the cause and all that.
Yeah, spot on. Andrew's got a question for you. Go ahead, Andrew.
Thanks. Yes, and a different kind of question. You've got a really geographically spread out system here with lots of different technologies. And with some companies, I see that they use very closely integrated systems. Rolls-Royce, for example, collects all its data centrally, whereas Bombardier in its orbiter system keeps the data in quite a distributed fashion. So what's your strategy for getting the data you need for your monitoring?
Okay, so I mean that we're still working on it. So I guess with devolve regions, now we can work on it as to suit the operating model. So for example, the talks might have we might work with the talks and they provide a service giving us the data. So that will be between that route. That talk will provide the data as a service. Measurement trains still provide data region. I mean, for the whole national railway. So it depends on what sort of data and how the package, the service.
That's an interesting blend. So you've still got quite a demand for central computing and archiving, but also blending in data as a service and maybe information as a service from TOCs and other operators.
Yes, or suppliers. Yeah.
Yeah. Thank you.
Thank you.
Thanks, Andrew. Anybody else got anything else? Oh, got another one in the chat. So around asset management and how do we in NR example of information, best practice, lessons learned on Rough Riders West Coast. How do we share? How are we sharing it from the East Coast?
Oh yeah, so because we are devolved regions, but we do have like sort of like an asset leadership group meetup. So it's 4 weekly. So then we share lesson learned from each region. For example, I've shared all these today, what I presented to them yesterday with the other regions. And the other regions, like for example, Western is using a lot of LiDAR data. So LiDAR data to, and then we're learning from them how they use it for gauging purposes and for track renewals purposes. So yeah, so different regions are pursuing different priorities.
Great, thanks. Brian's got a question now. Go ahead, Brian.
Yeah, thanks, Sin Sin.
Hi, Brian.
One thing I was interested in, have you found any sort of reluctance from the frontline staff to trust the data, particularly when they've sort of gone in and done some work that they believe is effective, and some of your plots there where they've been manually kangoing or packing point motors and similar clearly didn't work well, or the weld repair wasn't effective or wasn't as good. I think it's getting people to trust the data. Have you found any problems with the frontline staff sort of not accepting it almost because it isn't the answer they want, or
well,
it's critical of their work maybe is perhaps a bit unfair? Yeah.
Yes, I think it's depot dependent, because you need a depot who wants to embrace using technology and data. So they will then, you have to calibrate the data. Of course, you have to trust the data, as you said, but you have to calibrate it yourself or validate it yourself, and then you start trusting it. So some depots are not technologically savvy, so they won't use it. Even if you give it to them for free, they won't use it. But some depot will, and they will calibrate it and use it for themselves. Yeah.
Do you see a way of rolling it out wider, perhaps to the less, as you say, tech savvy, or is it going to sort of word of mouth type thing, or is it something that once you're happy with the data that's coming back, you start to sort of enforce it almost as a...
Yes, I mean, data like that, you need to have someone to own it and then monitor it themselves, because I find it, I think it's difficult for the region, for example, for me to monitor the data and then tell the depot what they need to do. So they have to own the data, own the system, and use it for themselves. And they are the one who knows their patch. You know, for example, the UGMS, the dip angle, they know where it is, and they know exactly what the component is actually. Yes. Or else the region can't tell them.
Yes, yeah, no, it's an interesting one, because there's a sort of tendency that it all gets collected centrally and then sort of issuing work requirement or work or waifs or similar out to the things, and I think that's where we've struggled perhaps in getting people on board there to trust the information, learn what it's telling them, and then make use of it. But it can be a slow way of getting things out there. But no, it's good that you're getting areas now starting to really take it on board. It's excellent. Thank you.
Yes, that's what we need, like diversity of people in depots, very young ones, young people who can use the iPad very well. And then we need the more experienced one who knows, oh, I know how to fix that, you know, I know the course, you know. And so you need a mixture, I think.
Excellent. No,
Thanks,
you.
Brian.
Right. Thanks, Brian. Good question. Anybody for any more? I bring the meeting to a head. No, I was just immensely interesting. Sin Sin. Can't fault it. I'm a bit of an early adopter myself, so all that new technology and stethoscopes and all sorts of stuff in there, really interesting. Couldn't fault it. And that time just flew by as we were trying to understand all the new things that are going on, and then the extras at the end. I couldn't believe that there was so many things that that are still ongoing. So really exciting times, I think, in the industry. It does sound like data's probably our enemy at the moment, is the volume of it and trying to get it into information. But yeah, it was really great. And yeah, if everybody could follow me in thanking Sin Sin in the usual way. Thank you.
Thank you. Thanks, Ian. Thank you for having me.